Hello today. I'm going to do talk about radio communication today and the history of that today, if that's all right. Um, the the ionosphere is composed of three main parts: the D, E, and F regions. And I just want to show you this here, just so we start here. I've got that there. And on the other side, I've got this. And I'll just go through it here for you. The troposphere is the region that we walk around and do things like that. And then the troposphere. So yeah, that's right. The troposphere is the region we walk around, and it's around that region. And even if you go to the high altitudes of mountains, I still think that's in the troposphere. Yes, it is. Sorry, yeah, it is in the troposphere. Then you've got the stratosphere, and the stratosphere starts at 4.3 miles around the poles. Sorry, around the poles. And then at the mid-latitudes, like latitude 45, the stratosphere starts there. So it's a higher altitude. It's at a higher altitude around the mid-latitudes, and then around the equator, it's even higher where the stratosphere starts and the troposphere ends. And at the upper end of the troposphere is a region known as the tropopause, and then the stratosphere commences at the different points around the parts of the altitude skies around the globe, if you know what I mean, which I've already said. The mesosphere starts at 31 miles. The lower part of the mesosphere starts at 31 miles, and the upper part of the mesosphere starts at 53 miles. And then you've got the thermosphere, which starts at 62 miles and finishes at 310 miles. And then you've got a region called the exosphere, and that starts at 310 miles. And it actually, the moon is actually 238,000 miles away from where we live. But yeah, that's right. So it's 238,000 miles, and it does vary. The distance between us and the moon varies at times, so it might be a little bit closer and further away. And the exosphere starts about 310 miles above sea level, and halfway into the exosphere, you're halfway to the moon, I think. So that's what I wanted to show you. The D layer of the ionosphere, and I'll talk about the ionosphere a bit later on, but the D layer of the ionosphere, it's the upper part of the mesosphere. And the E layer is the lower part of the thermosphere. And the F layer is the upper part of the thermosphere. And you've got F1 and F2. And one of them's 386 miles above sea level. F1 is, and F2 is 248 miles above sea level, and that's it's in the thermosphere. So I just thought I'd mention that. So if I just thank you for that. Yeah. So the if we talk about the ionosphere, it's composed of three main parts: the D, E, and F regions. It causes molecules to ionize, and its electric current is induced by the interaction between charged particles and the magnetic field. So ionosphere, electrically charged atoms and molecules. So I just thought I'd mention that to you. If I talk about if I just want to say creating ions in the ionosphere. I just wanted to say that to you. And to dislodge an electron from a neutral gas atom or molecule sort of radio propagation to distant places on the Earth. I just want to talk about that. Um, so the atmosphere is partially or fully ionized and contains a plasma which is that's right. So yeah, I just wanted. It's about removing electrons, and the ionosphere. It exists primarily due to ultraviolet radiation from the sun. So I just thought I'd mention that. So I just wanted to say that to you. Right. So yeah, enabling radio waves to be refracted and thus be received beyond the horizon. I just wanted to say that to you. So, right, the during the day, it's ionized by solar radiation. We're ionized by solar radiation, and I think at night is it cosmic rays? I don't know. Something. It's like that. The ionosphere is ionosphere's existence is due to radiation from the sun, so yes, so the it's an ionosphere is an electrically charged layer of the upper atmosphere. So I just wanted to say that to you. Yeah, so during the day, the ionosphere is ionized by solar radiation, and that's right. So. Right, I just wanted to say that to you. Yeah, so if I talk about shortwave radio communication, radio waves in the shortwave band can be refracted from a layer of electrically charged atoms in the atmosphere called the ionosphere. It reflected back to Earth at great distances beyond the horizon, called skywave or skip propagation of radio waves. Shortwave radio is used for very long distance communication. So I just thought I'd mention that. So yes, right. So the levels of ionization fall at dusk time. So I just thought I'd mention that to you. Yeah. So I just thought I'd mention that. Medium wave radio waves can easily be received many hundreds or even thousands of miles away, as signals will be reflected by the higher F layer. So signals can be reflected by the higher F layer. This can allow very long distance broadcasting. So if I talk about AM, amplitude modulation. I think amplitude modulation. Radio waves in the frequency range from 540 to 1600 kilohertz, KHZ initials. AM signals travel hundreds of miles by reflection from the ionosphere, and come receive back to Earth. So I just thought I'd say that to you. It's the phenomenon called skywave propagation. So I just thought I'd mention that to you. So they that's right. If I just reiterate again, AM radio waves in frequency range from 540 to 1600 kilohertz (kHz). AM signals travel hundreds of miles by reflection from the ionosphere. And that's right. So at night, I think the D layer disappears at night, and in the winter time it's not around as much. And obviously in the northern hemisphere it would be, November to March time or whatever, and obviously in the southern hemisphere it would be March to sort of September, when when it's topsy-turvy and we have our winter, when we have our autumn and winter, the D layer and disappears at night time, and also when the sun sets, because the D layer relies on the sun in the day, and the E layer gets weakened, so the F layer then comes into its own a bit more then. So I just thought I'd mention that. So the D layer vanishes, and the E layer it gets weaker. It becomes weaker. So I just thought I'd mention that. So medium waves also reflect off charged particles in the ionosphere and return to Earth at much greater distances. This is called skywave propagation. Skip propagation. So medium waves can also reflect off charged particles in the ionosphere and return to Earth at much greater distances. This is called skywave propagation. So at night and in winter months, the lower ionospheric D layer disappears. So that's right. That's right. I just thought I'd mention that to you. Medium wave signals, which have that's right. They have wavelengths of about 300 meters. Don't they? They can be received long distances from the transmitter because they are reflected from the ionosphere, which is an electrically charged layer in the Earth's upper atmosphere. However, these signals are usually very fuzzy. And that's right. So I just thought, so medium waves, synonymous with can be received long distances from the transmitter because they are reflected from the ionosphere, which is an electrically charged layer in the Earth's upper atmosphere. So that's what So if I just say AM is used for long distance transmission. AM service generally limited to a radius of no more than about 100 miles. But during night time, AM signals can travel over hundreds of miles by reflections from the ionosphere, and a phenomenon called skywave propagation. So I just thought I'd mention that to you. So let's just see. Let me just see what else. Right. AM waves are used to carry commercial radio signals in the frequency range from 540 to 1600 kHz. The abbreviation AM stands for amplitude modulation. That's right. And FM radio waves are also used for commercial radio transmission in the frequency range of 88 to 108 MHz, megahertz, I think. FM stands for frequency modulation, so I just thought I'd mention that to you. I'll just right. So if I just talk about some other things now. HF is high frequency. HF stands for high frequency. 3 to 30 megahertz, MHz. Long range communications, that's right. Shipping, aircraft, world broadcast communications. Use involves reflecting the signal off the ionosphere back down to waiting and receiving stations. So prone to atmospheric changes causing fading and noise. So I just thought that range from 500 to thousands of kilometers. Very high frequency, VHF, is 30 to 300 megahertz. Medium range communications, and the range is 70 to 100 kilometers. That's what. And then I've got UHF here, ultra high frequency, 300 to 3000 megahertz. Right. So I don't think that one. Is that one? I'm not sure. Yeah, so I just thought I'd mention that one. Sorry. Right, so I'll just talk about just something else now. Or the same things. Just a minute. Sorry about this. Right, I just thought of let's just talk about it here. Um, right. So yeah. So if I talk about AM, medium wave, AM, radio tends to travel this way for short to moderate distances. Right. This affects. Right. Okay then. And I'm going to talk about the ionosphere, an electrically charged part of the Earth's upper atmosphere. And come back down to the ground again. The effect works best at night, which explains why distant foreign AM radio stations are much easier to pick up in the evenings. During the daytime, waves shooting off the sky are absorbed by lower layers of the ionosphere. At night, that doesn't happen. Instead, higher layers, that's F1 and F2 of the ionosphere, catch the radio waves and fling them back to Earth at great distances. So I just thought I'd mention that to you. Yeah, so at very low frequencies, and I'm not sure, does this include AM and medium wave and long wave? I'm not sure. I think it might. Yeah, so at very low frequencies, in the very low frequency to extremely low frequency bands, an Earth ionosphere waveguide mechanism allows even longer range transmission. So I just thought I'd mention that. Right. The discovery around the 1920s of the ionospheric reflection or skywave mechanism made the medium wave and shortwave frequencies useful for long distance communication. So I just thought I'd mention that to you. Yeah, so and obviously the advent of satellites superseded this way of communicating with radio communications and stuff, and it was superseded by satellites. But before the invention of satellites, I suppose man-made. The moon is a natural satellite, and man-made satellites superseded this way that I'm talking about. And I'll just mention. Right. So yeah. Right, the transmitter produces a signal that actually travels through the air along a wire or through an optical fibre. In the case of radio waves, it involves an aerial. The receiver accepts the signal sent by the transmitter. It can be an aerial, or it can be at the other end of a wire or optical fibre. So I just thought I'd mention that. Shortwave broadcasts can be easily transmitted over a long distance. Of several thousands of kilometres, including from one continent to another. So short wavelength waves for long distance transmissions. Yeah. Right. So very low frequency is 3 to 30 kilohertz. HF, high frequency waves, 3 to 30 megahertz, reflected by the ionosphere, and thus they are also usable for long range communication. So the high frequency band is a major part of the shortwave band of radio communication. So I just thought I'd mention that to you. I just thought, yeah. Yeah, so in radio communication, skywave or skip refers to the propagation of radio waves reflected or refracted back toward Earth from the ionosphere, an electrically charged layer of the upper atmosphere. Since it is not limited by the curvature of the Earth, so obviously it's not to do with line of sight. It can travel vast distances. Things I've just said. So yeah. If I just thank you for this. I'll just get some more. Right. If I just. Right. Okay then. So let's just. Right. Right. High above the surface of the Earth, um, lies a region known as the ionosphere. At these great heights, the atmosphere is very thin, and as the ultraviolet radiation from the sun reacts with the well-spaced molecules of air, ions are produced, tiny particles with a small electrical charge. Until the era of the artificial satellite arrived, this layer of charged particles played an important part in radio communications. So in December 1901, Marconi built a powerful wireless set, and succeeded in sending a signal from Cornwall in England to Newfoundland on the east coast of Canada. The scientific, yeah, that's right. So, right. So yeah, as it happens, the waves are slightly bent or refracted by the atmosphere. So the so-called radio horizon is somewhat further away than the optical horizon. Right, okay then. But ions only reflect the relatively long wavelengths used in ordinary radio broadcasts. Shorter waves, such as those used for television, pass through the barrier unaffected. Right, okay. Now, let me think. Nowadays, of course, intercontinental radio and television communication are conducted via satellite. Very short wavelengths are used, which allows the waves to pass through the ionosphere undisturbed. So I just thought I'd mention that to you. Right. Yeah. So Marconi proved to the world that that's right. So. Sorry. Marconi electrified the world in 1901 by sending radio signals across the Atlantic. He proved that the upper atmosphere is electrified. That's right. So I just thought I'd mention that to you. So ionized by solar radiations, reflections, atoms ionized by solar radiation. Entire ionized region in upper atmosphere, the ionosphere. So yes, I just thought I'd mention that. Ionization of ionosphere layers is mainly due to ultraviolet radiation from the sun. So obviously the D and F layers rely on in the daylight of the being ionized from the sun. The sun is like some sort of light, isn't it? Almost like a lamp for us when the sun goes down, and when we used to try to illuminate the world at night before electricity, it was messy job, wasn't it, with candles and stuff like that, and not very and very dangerous as well, because it fires could happen very easily. So yeah, it's that's right. So radio propagation is the behaviour of radio waves as they travel or are propagated from one point to another. Radio waves are affected by the phenomena of reflection, refraction, diffraction. So that's right, reflection, refraction, diffraction, absorption, polarization, and scattering. So I just thought I'd mention that to you. Okay. At low frequencies in the MF, in the medium frequency, low frequency and very low frequency bands, due to diffraction radio waves, which can bend over obstacles like hills and travel beyond the horizon. That's right. So I just thought I'd mention that. Medium waves and shortwave frequencies, MF and HF bands. So MF is short for is medium frequency, and HF is high frequency bands. Radio waves can refract from a layer of charged particles, ions, in the upper atmosphere called the ionosphere. This means that radio waves transmitted at an angle into the sky can be reflected back to Earth beyond the horizon at great distances. This is called skywave propagation. So I just thought I'd mention that to you. Yeah, radio engineering antenna is the interface between radio waves propagating through space and electric currents moving in metal conductors used with transmitters or receivers. So I just thought I'd mention that. A medium wave used for AM broadcasts, I think that's right. So I just thought I'd mention that. If I talk about the ionosphere, an electrically charged part of the Earth's upper atmosphere, and comes back down to the ground again. This effect works best at night, which explains why AM radio stations are much easier to pick up in the evenings. Right, that's right. During the daytime, waves shooting off to the sky are absorbed by lower layers of the ionosphere. At night, this doesn't happen. Instead, higher layers of the ionosphere catch the radio waves and fling them back to Earth, giving us a very effective sky mirror that can help to carry radio waves over very long distances. So I think that's sort of when the D and the E layers disappear. The D layer disappears at night, and the E layer becomes weakened. I think something like that. And then of course you've got F1 and F2 in the thermosphere, which I showed you earlier on. The antenna, A-N-T-E-N-A-A, so that's A-N-T-E-N-N-A, sometimes called an aerial. It's the metal rod or dish that catches radio waves and turns them into electrical signals, feeding into something like a radio or television or telephone system. Antennas like this are sometimes called receivers. A transmitter is a different kind of antenna that does the opposite job to a receiver. It turns electrical signals into radio waves so they can travel sometimes thousands of kilometers around the Earth or even into space and back. Antennas and transmitters are the key to virtually all forms of modern telecommunication. So I just thought I'd mention that. Right, line of sight propagation at low frequency, below approximately 3 megahertz, due to diffraction. Radio waves can travel as ground waves, which follow the contour of the Earth. This enables AM radio stations to transmit beyond the horizon. Additionally, so that's right, frequencies in the shortwave bands between approximately 1 and 30 megahertz can be reflected back to the Earth by the ionosphere, called skywave or skip propagation, so thus giving radio transmissions in this range a potential global reach. So I just thought I'd mention that to you. Yeah. So the discovery around 1920 of the ionospheric reflection or skywave mechanism, that's right, made the medium wave and shortwave frequency useful for long distance communication. So I just thought I'd mention that. So ionospheric is spelled IONOSPHERIC. So I just thought I'd mention that to you. AM radio waves, waves used to carry commercial radio signals between 540 and 1600 kilohertz. So I just thought I'd mention that. Right, radio waves designates a proportion of the of the electromagnetic spectrum having frequencies ranging from 300 gigahertz to 3 kilohertz. So yeah, that's quite a big range there, isn't it? Vast range. Right. Different frequencies of radio waves have different propagation characteristics in the Earth's atmosphere. Long waves may cover a part of the Earth very Long waves may cover a part of the Earth very consistently. Shorter waves can reflect off the ionosphere and travel around the world. And much shorter wavelengths bend or reflect very little and travel on a line of sight, so that they don't go very far as well. I think that could be FM actually. That doesn't go very far. Sort of line of sight, antenna, transmitter, and receiver can see each other. I think. I mean, I'm not 100 on this, but you know, I think I'm more. I'm not sure. Yeah. So when wave propagation is any of the ways in which waves travel. So I just thought I'd mention that. Right. Electromagnetic waves propagate at the speed of light in a vacuum. So I just thought I'd mention that. Yeah. Skywave propagation Electromagnetic waves emitted by transmitting antenna are received after being reflected from the ionosphere, are called sky waves, and this type of propagation is called skywave propagation. So I just thought I'd mention that. And before I... Yeah, because waves are... Right, I just want to say one more thing. Because waves are reflected, they can reach receivers that are very far away. So I just want to... Just... Before I go today, I'm just going to... yeah, so... if I just talk about... Yeah, so AM signals have wavelengths 100 times bigger than FM signals. Because of the longer wavelengths, AM waves reflect off a layer of the upper atmosphere called the ionosphere. So I just thought I'd mention that. Right, in the presence of the magnetic field, the ionosphere is a refracting medium. In 1901, Marconi succeeded in transmitting radio signals across the Atlantic of the reflecting layers. That's right. And might be said to mark the beginning of the ionospheric ionosphere. Right. It has now virtually I think the satellites have superseded satellites have superseded that what I've been talking about. It's been so it's a bit obsolete now, I think. But I'm not sure. So I just thought, anyway, I just want to write something down for you very quickly. Thank you for your patience today. Right. Thank you for your patience. Just want to say one more thing, and then I'll leave you. Right. If I just write this down for you before I go today. Right. Okay, I just want to... Right, sorry about this. a minute now. Uh, um, Right, just want to quickly say, yeah, okay, thank you for your patience today. I just want to show this to you very quickly. Yeah, so extremely low frequency, like that, just show you that. And yeah, ELF is abbreviated to extremely low frequency. The frequency is 3 to 30 hertz. The wavelength is vast. It's 10,000 to 100,000 kilometers. That's the wavelength, and it's this one is guided between the Earth and the D layer of the ionosphere. So ELF is guided between the Earth and the D layer of the ionosphere. The super low frequency here is 30 to 300 hertz there, and the wavelength is 1,000 to 10,000 kilometers. 1,000 to 10,000 kilometers, and then the ultra low frequency. It's guided between the Earth and the ionosphere, and it's 300 to 3,000 hertz. So yeah, it's 300 to 3,000 hertz. So I just thought that's what I thought. I put ultra low, and then you've got very low frequency after the ultra low, and then you've got the low frequency, which is yeah, that's right. It's guided between the Earth and the ionosphere. And the medium frequency is EF layer ionospheric refraction at night when D layer absorption weakens. And then the high frequency, which is the short wave, is E layer ionospheric refraction, and F1 and F2 layer ionospheric refraction. So I just thought I'd mention that to you. Yeah, it's been quite challenging talking about this actually today. So I just thought, I found it quite hard talking about it. So there you are. Anyway, thank you for watching me anyway, and if you like what I'm doing, could you subscribe to my channel? That's very kind of you. That's very nice if you do. So yeah, ELF is extremely low frequency, super low frequency, ultra low frequency, very low frequency, and medium frequency, sorry. Yeah, okay then. So yeah, thank you very much for listening to me today. That's very kind of you. Thank you very much. Thank you. Bye.